Okay, cool. Let's go ahead and get started. Thank you all for coming. You are currently with the AI Club, and today we'll be working and learning a little bit about supervised learning. So, just to preface, this is an introductory meeting. You guys, if you have no experience with supervised learning, we're going to be learning about the concepts, and we're also going to learn how to implement our own model. So, without further ado, let's go ahead and get started. So, on the agenda for today, I'm going to go ahead and introduce who I am first. And then we'll go ahead and delve into what is supervised learning. And from there, we'll talk a little bit about the machine learning algorithm we will be implementing, which is the k-nearest neighbors algorithm. And finally, after we've talked about the concept, I'll show you guys how to implement your own model using the k-nearest neighbors machine learning algorithm. So about myself, my name is Adwith Malpe. I am a 4+1 student here at ASU. Currently working on my master's in computer engineering with a concentration in autonomous systems and robotics. I am the president of the Artificial Intelligence Club here at ASU, and I'm also an assembly member for GPSA. Fun fact about me is that I'll be interning at Goldman Sachs this summer as an operations analyst. If you guys want to know more about me and some of the projects that I've worked on in the past, or even some of the articles I've written before, go ahead and check out my website. I'll share these slides towards the end of the meeting on our Slack channel for those of you who want to go through the information. It's really helpful. But yeah, that's a little bit about me. So let's go ahead and delve right into what is supervised learning. So before I talk a little bit about what it is, I just want to know, feel free to unmute yourself or state it in the chat. Does anybody want to share what their definition of supervised learning is? Feel free to go for it. Basically, supervised learning is a type of machine learning. There are three branches in machine learning: supervised learning, unsupervised learning, and reinforcement learning. With supervised learning, it's a branch that basically refers to a class of systems and algorithms that you're able to use to develop your own predictive model and train your model using given inputs and outputs. So basically think about it like a student, in this case, is your model, and you have a teacher, and the teacher provides the student with information and checks if the student is giving the right answers. The teacher will then correct the student and tell the student what's right and what's wrong. The student will then be able to learn based on his mistakes what's the right answer and how to get to the right answer, and then apply that to future problems they will be solving later on. So yeah, pretty much in short, supervised learning is where you just feed the model input data, and then you also feed it the correct output data, which is also known as labels. Let's go ahead and move on to the next slide. So what is the general process of supervised learning? Well, the very first step you need to do is you need to gather all your labeled training data. Labeled training data typically means that you're providing your model with known inputs and outputs. Giving your model the known input and output basically gives it feedback, meaning that you're telling your model, this is what the expected value is, this is how you get there. And you're training it and teaching it to learn from previous mistakes. Eventually, once you generate a high enough accuracy with that model, you can apply it to test data, which I'll be talking about in the next bullet point, which will basically mean that your model has been trained enough and ready to take on the real world. So after you've gathered your label training data, you want to split your data into three data sets. You have your training data set, your testing data set, and your validation data set. So the training set, as implied, is used to train the model to make sure that you minimize error, especially when testing your model on the test set. The validation set, I'm not going to show it in this implementation just because you guys can play around with that on your own at your own time. But essentially, the validation set is a really good data set you can use to measure the progress of your own model. You can use it to identify the cutoff point in the training algorithm, basically to identify what the best accuracy of the learned model is, without having it be overfit to the data. And finally, you have your test set, which basically is like a part of the data set that you use to test how effective your model is, whether it's able to make the right predictions or not. And basically, this test set is data that your model has never seen before, so you'll be able to make predictions that way. Once you finally split all your data into the data sets required, you can finally train and then test your model on those data sets and evaluate its performance. That's the general procedure. It comes when working with supervised learning. So what are some of the applications of supervised learning? Well, in supervised learning, there's two different branches you can really delve into: classification and regression. So some of you might have actually worked on these projects already. Some of the common projects within classification include fraud detection, email spam detection, diagnostics, image classification. Fun fact, I'm actually working on anomaly detection, which is similar to fraud detection in one of my courses this semester. And then you can also be working with regression. Some of those projects include risk assessment and score prediction. Now, unsupervised learning is very different from supervised learning in the fact that you're not providing it with the labels. Essentially, the model is learning for itself based on the data. And some of the projects that you're working with in unsupervised learning are within branches such as dimensionality reduction and clustering. So in dimensionality reduction, you're typically working with projects such as text mining, facial recognition, big data visualization, and image recognition. And in clustering, you can work in projects that are typically associated with biology, city planning, and targeted marketing. Reinforcement learning, like I said, is that third branch of machine learning. You can work with gaming, finance sector, manufacturing, inventory management, and robot navigation. But for this workshop, we're going to be talking a lot about supervised learning. So here's a really useful diagram that I found that really explains supervised learning at an elementary level. So you have your input raw data set where you're feeding your algorithm information and you're training you're using that model, you're training your model with that input raw data set and the expected values so that it understands. Now, you're only using a certain portion of your data set to train the model. Usually I like to do a 90% to 10% ratio, where 90% of the data you're using is to train the model and 10% of that data is being used to test the model. So once you have trained your model and it's received a pretty good, decent accuracy, you can finally apply your model on the test data set. So in this case, you can see the robot accurately predicts that whatever the input was, in this case, a tomato, was a tomato. Awesome. So we're going to go ahead and talk about our supervised machine learning algorithm. So in this case, it is the k-nearest neighbors algorithm. Did anyone have any questions and comments so far? Am I going too fast, or anyone want to add anything so far? Okay. Well, let's get started then. So with k-nearest neighbors, it's essentially a supervised machine learning algorithm where you have a primary assumption, where you basically expect that similar things that exist in close proximity are related. So what do I mean when I say that? Well, let's go to the next slide real quick. So here's a simple illustration, right? We have three data objects. We have red points, green points, and blue points, right? So we could see visually, we could see these groupings of red points, blue points, and green points. But the computer doesn't see that color. It sees points, and we want to make sure that we train our model to basically determine what an inserted data point will be recognized as. So you see this black data point right over here. That's basically the data object that we want to classify. So when we're classifying this data point, we're going to see which one is it the closest to. That's how k-nearest neighbors works. Basically, k, which is a hyperparameter that represents the number of closest neighbors you want to compare your data object to, will be used. So in this case, I set my k to be 5, right? Meaning I want what are the 5 closest neighbors. And in this case, we could see that we have 3 points here, which are green. Those are pretty close. And then we have 2 points here, which are blue. So how did I know that those are the closest points to the inserted data object? Well, basically, we use the Euclidean distance formula to determine what are the closest points to the inserted data object. And from there, we could see if the Euclidean distance is within a certain threshold, like say like 0.5 or whatever your threshold is, it'll determine what the nearest neighbors are, which are k. Okay, so now we could see that we're using an odd number of neighbors. Typically, when you're working with your hyperparameter k, you want to pick an odd number, because if you were to think about it like this, right? Say we were to use an even number for our number of neighbors, and we come across an event where we have two neighbors here. You can disregard this third point out here. You have two neighbors here and you have two neighbors here. And when you have those two neighbors, you can't really tell whether it belongs to the blue grouping or the green grouping. So that's why you usually use the third, you use an odd number of neighbors, because that kind of like breaks the tie. And essentially we can see that we have the three data points here, the three green data points here are closer to this inserted data object here. Therefore, we can classify it as a green data point. That's basically how k-nearest neighbors work. So we're looking at the Euclidean distance. How close is an inserted data point to a group of other data points? And we can say that that data point is similar to the group of data points that it's the most closest to. Coming off, if that doesn't make any sense or if you guys need further understanding, but that's pretty much how it works. So like I said, Euclidean distance is used for the measurement. Now there are certain advantages with k-nearest neighbors. The algorithm is very easy to implement and it's versatile, so it can be used for classification, regression, and search. However, there is a disadvantage, and that's when the algorithm gets slower as the number of examples, predictors, and the number of independent variables increase as well. Cool. And I'm going to be sharing these slides. Basically, I included this step-by-step process of how the KNN algorithm works. You guys are able to view it whenever you want. I'll be sharing this on our Slack. Cool. So now that we've gone over the concepts of supervised learning and the k-nearest neighbors machine learning algorithm, we're going to go ahead and actually delve into our implementation. I found this really cool diagram just to help you guys distinguish between supervised and unsupervised learning. Supervised learning, in this case, you could see a little robot just kind of being taught by an instructor, or in this case, a programmer. And unsupervised learning is basically where the machine or the robot is kind of learning by itself. It's learning on its own from the input data, which is in this case represented by the book. So without further ado, just to clarify before I move on to the implementation, is everybody with me so far? Are we good? Is my mic off this time? I don't think so.
Yeah, it makes sense.
My mic was off this whole time?
No. Your mic was on. It just like, everything makes sense.
My speakers were off the whole time.
Oh, really? Okay.
Yeah. My bad. Was I speaking over you, Michael?
No. You were.
I'm so sorry. I didn't know. That's my bad. I was wondering. I was like, why is it so quiet? Oops. Okay. Anyways, apologies. Let's go ahead and jump right into the implementation. So the first thing you guys want to do is go to UCI's machine learning repository. I should probably drop the, give me 1 second. Let me drop this link in the chat. Okay, cool. So this is the machine learning repository we'll be using. UCI's machine learning repository is really nice. You can also use Kaggle. I like UCI's because I've used it for quite some time now. And the nice thing about it is that most of the data sets are pre-processed, meaning that like you don't really have to perform too much data cleaning of your own. It's really neatly formatted in data or CSV files, and you don't have to spend too much time worrying about that. This really helps you when you're just trying to learn how to implement your own machine learning model on your own first before you do any data cleaning. So our implementation today is going to represent a classifier that evaluates a type of car based on its class. So what we're going to be doing is we're going to try to predict what class a certain car is based on certain attributes. And the attributes we're going to be evaluating the car on include typically who's buying. Do we have a lot of consumers buying at a very high rate, medium rate, low rate? We're going to look at maintenance. Is the maintenance of the car very high, medium, low? The number of doors the car has, the number of people the car can seat, the size of the trunk or the lug boot in this case, and then the safety rating. So is it low, medium, or high? Yeah, so these are the attributes we're going to be using to predict whether our car is unacceptable, acceptable, good, or very good, right? And basically, if you guys want to, now that you have the link sent in the chat, you can read more about this data set. It has all the information right over here. The first thing you are going to want to do, go to the data folder and click on car.data. Essentially, this is the file that has all of the, what is it called? All the values that we want. So I will show you what it looks like. Let me just open up VS Code. You can also open it up on a text editor or a notepad or whatever. I just like using VS Code because it's a lot cleaner. So give me 1 second. Michael, was there anything you wanted to add? I'm sorry. I'm so sorry again. Like my speakers were off.
Oh, I guess I think it would be interesting to talk about what would be, I guess, an optimal size for K. If you, I mean, I think it's what was I gonna say? I mean, did you? It was just a question that popped in my head. I mean, would you know what size K would be depending on the size?
That's a really good question. So when you're working with KNN, usually you want to be very careful with the number of neighbors you pick for K. So if you pick too many, for instance, if you pick an odd number that's really high, say I want to say like above 11, right? It really depends on it. I want to say it depends on your data set, because say if you have a really big data set, typically your value of K can be a little bit higher. But as you increase the number of neighbors, closest neighbors, K, what will happen is it'll start to look at all of these data points. So like, let's say if I do 7, right? Or let's say if I do 9, what it'll do is it'll look at these 5, but say the next closest point is red, right? Red, 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 red. And then what ends up happening is, say you have a pretty like say you have 3 or like 4, 3, and then 4, 3, and then 2. So typically it becomes a little bit harder to classify what group does that data point belong to. Does that make sense? Because you're looking at more groupings.
Right. Okay. Yeah.
Okay, cool. Sorry. Anyways, going back here. So I have the data file opened up here. So when you guys download that data file, you'll get this enormous car.data file, which you will find over here. And you can see in the website that I sent, so if I go back, it has 1,728 number of instances, meaning we have 1,728 values we can work with. And we're going to be looking at a total of 6 attributes. And we can see that our data characteristics are multivariate, which means we're looking at different, like multiple types of data, right? And we're developing our own classifier, as I mentioned before. Anyways, so getting back on track. So the first thing you guys want to do is, in this one instance, the data set was not fully pre-processed. You just want to insert the names of your attributes at the very top of the line. So you can type it, or you can write a line of code that inserts it manually. It's really up to you. I just figured since it's one line of code, I could type it into the text editor. So that's what I did. So the labels the attributes we're going to be looking at are buying, maintenance, door, persons, lug boot, safety, and class. That's all you need to do. Everything else is already in there, so you don't have to touch that. You just have to put this line at the very beginning. I just want you guys to know that this is being recorded. So if you want to follow along, you can check out our YouTube channel too and pause it there. But yeah, that's what you want to do. So now that we have our car.data file downloaded, we can go ahead and get started. Let me zoom in. Can you guys see this okay?
Yeah, we can see everything.
Okay, awesome, sweet. So the first thing you want to do is, I'm using Google Colab. I like working with Google Colab because you can work with many people on a certain file. It's a really good cloud computing IDE, and it does version addition as well. So say if you if you wanted to look at a previous version of code you wrote that worked better, you can go back in your history and use that code as well. So what I'm going to do is I am just going to upload my data file. Just give this a second. Cool. So our data file has now been uploaded. So the very first thing we're going to need to do is we want to import all of our libraries. So we're going to need pandas because we're going to be working with data frames. We're going to need NumPy because we're going to be working with arrays. We're going to need sklearn. Sklearn is a really useful machine learning library. So when you're working with different machine learning models, I would recommend using sklearn. And from sklearn, we're going to need shuffle. And this just gives us more functionalities that I'll explain later on as we go. And we're going to need k-neighbors classifier. And we're also going to need linear model and pre-processing. So there's something I want to emphasize going back to the data set. Notice how some of the values in our given attributes, are non-numeric and some of them are numeric. So for instance, buying, maintenance, lug boot, and safety, they're all non-numeric, right? They're all like text values. But if we look at doors, persons, those are numeric values, correct? So we want to use one type of value because when you're dealing with multiple values, it becomes more complex. And this is just an introduction, so we're going to stick with just numeric values for the sake of simplicity. So the thing we're going to need to do is we're going to need to convert buying, maintenance, lug boot, and safety, all of these values into numeric values. So like for instance, a 3 would represent very high, a 2 would represent high, a 1 would represent medium, and a 0 would represent low. Cool. And it's the same for the other attributes. So that's what pre-processing is going to be used for from sklearn. It's going to help us basically encode our non-numeric values into numeric values. Cool. So the first thing we're going to need to do is we want to read in our data from the data file. We could just use pandas.readcsv and store that into our data frame. Everyone calls it DF for short. And what we can do is we can check if we successfully did that by just calling the head method. And what that will do is it'll print the first 5 rows within your data frame. So you guys can see here, our data frame successfully printed. We have all the values for each of the following attributes with the numeric values as well, right? Cool. So that's what we do. That's the very first step. Step number 2, we want to pre-process our non-numeric values. And this is what I mentioned earlier, meaning that we want to encode all of our non-numeric values into numeric values, just because we're working with numerics. So what we're going to do is we're going to create a label encoder object by calling label encoder from pre-processing. And I'm going to store that into a pre-processed data variable. From there, I'm going to call this fit transform method. This fit transform method, basically what it does is it makes the conversion of all the non-numeric values into numeric values. And we're going to store those numeric values into a list, right? And I'll show you guys what it looks like once I run it. But we're going to store all of our values into lists. And you can see we have all of our variables here for every single attribute. So like I want to emphasize, basically everything that said very high, very high, very high, and all the non-numerics, we converted them to numeric. So now they're going to be represented by numbers. Now here you could see buying was originally a non-numeric attribute. Now it's a numeric attribute because when we print it out, the the label encoder method basically helped us make that conversion, and now it's a series of 3s, 2s, 1s, and 0s. Cool, awesome. What's our next step? Our next step is we want to split the train and the test data. So like I mentioned before, we're developing a classifier. We want to predict what class does the car belong to based on the following attributes: buying, maintenance, door, person, select boot, and safety. So what you need to do is you need to store that attribute or that label into a predict variable. You can call this whatever you want. I'm going to call it predict for the sake of simplicity. And what we're going to do is we're going to separate our data now. So the following attributes you're going to be using to train the model are your features, which are basically the properties of training your model. And you're going to store that in a variable called x, and it's going to be represented through a list. So that's why I'm using the list. I'm putting everything in a list. And then finally, class is our label, which is our output or our expected output that's going to be used to train the model. And we're going to store that into a list as well. So in our next line of code, this is where all the fun stuff happens. Basically, what we're doing is we're splitting our data set into training and testing data. Hence why we have xtrain, xtest, ytrain, and ytest. And just so you guys know, you really need to follow this kind of format, because if you do like xtrain, I think ytrain, like what happens is it messes with the formatting on how the data is stored into each respective variable. So you want to follow this format exactly. And what you're going to do is you're going to call the train test split function from sklearn using model selection. And what this will do is basically our test size is going to be exactly 10% of our overall size of our data set, right? And then we're going to use 90% of the size of our data or samples to train our model. Yes, you can increase the size of your test size, but typically when you increase the size of your test size, you're decreasing the amount of training data that you have that you can be using to train your model. And that usually doesn't like yield to the most optimal model. That's why you want to usually have more training data than test data. But yeah, that's what we're going to be using to split the data. And finally, if I were to print it out just to see what it looks like I said, everything is stored in tuples, and you have all the data values here respectively with xtrain and ytest. So now that we've ideally split all of our data, we want to go ahead and create and train our model. So now comes the fun stuff. What we're going to do is we're going to call the k-neighbors classifier, and this is the method we get after importing that sklearn library. We can call this method, and we can set the number of neighbors we want. In this case, I want 3 neighbors. Remember how we only use odd numbers of neighbors. So in this case, we're going to use 3 neighbors, and this is what's going to be used to create our model. And now when I want to train the model, all I have to do is fit the model on my xtrain and ytrain data. So we're basically feeding the supervised learning model all the known inputs and outputs from xtrain and ytrain. Finally, when we want to test and see how accurate is our model based on the actual test data, so xtest and ytest, all we have to do is call the score method on the xtest and ytest, and it will evaluate your accuracy. And yes, I will share this with all of you right after this workshop. But yeah, anyways, getting back on track. So yeah, this will help us compute the accuracy. All I did was multiply by 100, and I rounded up by 2, and it gives us an accuracy of 87.28%. Cool. So now let's go ahead and what we're going to do is we're going to apply our model on the test data. I just want to see what are the values what are our predicted values based on the xtest data that we provided it with. And we're going to store that in predicted. Okay, so now we're on our final step, which is just displaying the results. So when we're displaying the results, we just want to print out the test data and the prediction, and then the actual value. So the test data is basically the sample input that we fed it. Prediction is what our model predicted the final outcome to be. And the actual value is what the actual outcome is. I'm going to go ahead and in this line of code, basically, I just stored all of our attributes in a list called names. I'll show you guys why I did that. This is basically, I'm going to be using it to convert our numeric values to non-numeric so that we can see whether the predicted value does match the expected value. But in this example, or in this block of code, I'm just going to show you with respect to numerics. So for base, we're gonna create a loop that loops through the entire test data, and it's going to show you what our predicted outcome was. So in this case, 0. What was our test data, which is provided right here, and what was our actual output, which is provided right here. So you can see here that we were accurate. We hit it. Our model predicted the right value as it matched the actual value. But since we only achieved an accuracy of 87.28%, we know that it's not going to be right all the time. There are going to be instances where our model is incorrect. So to avoid that, basically, you just want to keep training. If you want to have a higher accuracy, you just mess around with those parameters. You can increase the number of neighbors if you want to see if that'll make a difference. And you just keep on running it. And what it'll do is this line of code right over here will, wait, that's splitting it, sorry. This line of code will basically keep on testing the model with new sample sets, with 10% of new sample sets from our data set. So anyways, yeah, that's pretty much what it looks like in the numeric form. Like, okay, wait, here we go. Right here, we can see it was wrong. We predicted 1, but our expected value was 2. So we can see that we just need to work on improving the accuracy of our model to get the right value. Now, you guys might be thinking, okay, well, this is numeric values. Like, what does this actually tell me? Like, I thought we were trying to predict whether our class values were unacceptable, acceptable, good, or very good. So that's why I went ahead and created this list right here, because now what we're going to do is we're going to basically cast our values in that same for loop. So it's basically the same for loop, but this time I basically stored my predicted of I in my names list. And what it'll do is it'll go ahead and it will convert all those values that I was telling you about, those numerics, to the non-numeric. So it'll say unacceptable, good, good, very good. And we can see here our predicted value is unacceptable, our actual value is unacceptable. It made the conversion successfully, and therefore we can see that, like, okay, this is all of our data. It made the predictions, and we can see whether it was right or wrong. So all in all, that's it. That's really it. That's how you create your own model. There's nothing more to it. Obviously, you can do more with your model, and you could save your model. You can do a lot of that, but I didn't want to add too much because I just really wanted to focus on showing you guys how to create your own model. You can learn how to save your own model using the Pickle library. You can do that at your own downtime. But yeah, for today, that's really all I wanted to show, just how to create your model, how to evaluate and test your model, and how to train it. Apart from that, that's really all that I wanted to share with you guys. Does anybody have any questions so far? Okay, it looks like there's a question. If you keep running it, will it increase the accuracy? So it depends, right? Your accuracy won't, that's a great question. Your accuracy won't always go up. It depends on what you're testing your data on. So let me show you something. Basically, okay, right here. So remember how our test set is 10% of the data set, right? That 10% typically varies every time we run our code. So sometimes when we have the thing is, will it increase the bias of the model? Not necessarily, no, because it's being exposed to new data every single time. That's why we call it the test set. If you wanted to keep increasing the accuracy, usually that's what reinforcement learning works with, because it's learning from its past mistakes. But in this case, we just want to keep on training it on new test data to achieve a high enough accuracy. It's not going to look at the previous test. Well, at least in this implementation, it's not going to look at it. I didn't train it to do that. But once you achieve a high enough accuracy that you're happy with, you can actually save that model and apply it on different data sets, on different test sets that have never been exposed to before. For instance, if my accuracy was like a 95%, then yes, I would want to save that model and I could apply it there. But it really depends. The accuracy varies with respect to your changes in your test set. Does anybody else have any questions?
You had mentioned earlier that you changed some of the text stuff to you changed some of the text to numbers. Does k-nearest neighbors work if you actually were inputting text, or do you have to input
I've
numbers?
never worked with it when you're working with non-numerics. I'm sure you can. Yeah, I'm sure you can use it with respect to um, non-numerics. It's just there would be that would be a very different way. Something that I haven't really worked with before.
Okay, just wanted to.
Even when we use the same test data again and again to train it without adding more data. So you're asking, won't that increase the bias of the model even when we use the same test data again and again to train it? Well, see, the thing is, I want to say, okay, so when it comes to bias, you have to keep in mind that okay, well, that's a very good question. I'm just trying to think of the best way to answer it. It's overfitting to a particular data set. Yes, exactly. So the biggest thing is when we want to avoid overfitting to a particular data set or avoid the whole bias concept, we typically use our validation data set, and that will be used to help us avoid overfitting and developing the best accuracy for the model. In this case, I didn't use the validation data set. Validation, not development. Validation data set. That's something you can kind of look on your own. In this case, I'm only using the train and test set. When it comes to overfitting, you usually work with a validation data set. It was a relatively short meeting, I know. I just wanted to show you guys how to create that model.
Yeah, just one question. You had mentioned earlier that there is a YouTube channel. What's the name of that YouTube channel
Oh
so
yeah.
I can go ahead and follow it, because I'd
If
love to take a look
you
at some
if
of your
yeah,
videos.
all you got to do is if you go to YouTube and just type ASU's Artificial Intelligence Club, that'll be the first thing that'll pop up. There's only one of us, so you won't miss it.
Awesome, thanks.
So you mentioned like from my understanding, when you choose a certain point for like the nearest neighbors, right? You're essentially creating these vectors, right? And you calculate the Euclidean distance
Yeah.
from one point to another. Wouldn't it like when like I know that there are, because of the nature of how like you calculate the distance, there's different ways to calculate distances, and by that very nature, there will be different ways to like partition like each um, class, like you would classify based on those distances.
Mm-hmm.
uh, if there are like what if is there any distance formula that we can implement like besides besides the Euclidean distance?
That's a good question. I believe there is. I'm not too familiar with it. I know Euclidean distance is typically the most popular, especially when working with k-nearest neighbors in developing classifiers. But I do know that there are other formulas you can use. I'm just not too familiar with which ones.
Okay.
But yeah, apart from that, that's pretty much all for today's workshop. If you guys, this meeting, like I said, is going to be recorded or is recorded, so it'll be posted on our YouTube channel. You guys could follow along there, and hopefully I went slow enough to the point where everyone can kind of follow. I'll also share this notebook on our Slack channel. It has all the comments, all the steps, so you can follow that respectively as well.
I have a question.
Yeah.
If we increase the number of neighbors for the KNNs, does that necessarily increase the accuracy?
No.
Is there a sort of relationship that you can map?
It doesn't. Hold on one second. Is there? Let me show you something. Yes, I will post the link in the Slack channel. Just one second. Give me one second. Let me go back to this example. Okay. So here we go. One second. So in this diagram right here, right? So if I were to increase my number of neighbors, K, to say like 7 or 9, right? What can potentially happen is it can kind of mess with your groupings a little bit. So say if my data point was like right here in the middle between all three groupings, right? what could potentially happen is it'll identify the closest neighbors to between all three groups, but then it becomes that much more complex when trying to um, identify what is your data object the most similar to, just because your group, it kind of messes with your groupings. So typically it really depends on the number of groupings you have. You want to pick your number of neighbors respectively.
Okay.
Does that make sense?
Yeah.
Okay, cool. Awesome. Anyone else?
I'm guessing if you had a larger number of groupings, you'd like to keep the number of neighbors to a lower odd number.
Yeah, like I said, it depends on the data set. You can ideally play around and see what number of neighbors yields really works the best for your model. And you'll know that by evaluating your model and determining which is the highest accuracy and which one doesn't.
Got it. Thank you.
Yeah.
I was just curious. So, is there a data size that you would just not consider using KNN?
Is there a data set where you consider not using KNN?
Like a size of a data set that you would
that's a
where
good
you would just cut it off, you know?
Oh, no, that's a great question. That's actually funny because in one of my current projects, James can vouch for this as well. He's on my team. When it comes to large data sets, there are certain models you use that are more efficient, that are optimized for larger data sets, and that don't work best for other data sets. So in this case with KNN, it really, like I said, it depends. I'm still pretty new to determining what's the best data set and what's not. Like for instance, we're working on another project which is related to LSTM, and our data set has around, I want to say, 6 million rows of values. And even for LSTM, which is a type of like AI, it it takes a very long time to compute. So I wouldn't say there's like a definitive value of number of values you can use that works best for k nearest neighbors, but you'll learn a lot more about that when you take data mining. It's a really interesting course, and it's very, very, I want to say, there's no right or wrong answer.
Gotcha. Is that LSTM like the neural network?
Yeah.
Is that on your YouTube?
It's not yet. No, James and we started the project like a couple weeks ago, so we're still working.
Cool. All right, thanks.
Yeah, no problem. Yeah. Just running it based on the number of epochs that we used, it took around 3 minutes per epoch, or not 3 minutes, excuse me. 3 minutes per epoch, and there was a total of 10. So it took 30 minutes just to run one cell block of code for our LST. So it was not fun. It took a while. But yeah. Does anybody have any final questions? If you guys have no further questions, you're free to go.